So anyway, this delta H vaporization is a constant by T square T star to T. Yeah, tell me something. My variable is log P. Yeah, that's it. Bz. So I have to start from Z1 to Z5. If you find that problematic, actually you could go to the first expression dP by P and integrate that one. So what I'll have over here would be if I integrate, then log of P by P star should be equal to delta H vaporization by R with a minus sign because I have a T square over there. Sorry, 1 by T minus 1 by T star. Right? And then I will put an exponential, let me call this as pi. So then I can put this like P is equal to P star e to the power minus chi. Right. Now, as I increase the temperature, this value goes down. Right? It's a negative number anyway. So this is anyway a negative number. Right? So I increase the value of P. This one goes down. Right? So this entire thing pi becomes a negative number. It becomes more negative as I increase the value of temperature. And I have a minus side, which means P to the power a positive number. So it's going to blow up exponentially. Now, depending on the value of delta H vaporization, this particular exponential growth will be decided. And if you look at the phase diagram, these two, both the solid gas and the liquid gas, they look more like exponential growths. Right? So, in fact, the liquid gas would be dependent on delta H of fusion, which is much higher than delta H of liquid gas would depend on delta H of vaporization, which is much larger than delta H of sublimation. Or the other way around. Sublimation is larger. So the exponential growth over here should be much larger than this one. Yeah, sublimation is fusion plus vaporization, essentially. Right? So you can kind of predict these curves. They may not interact at, all these curves may not intersect at the triple point because I am dealing with each and every curve separately. And I am taking some approximations over there. They might interact at some point, but it's quite unlikely that they'll interact at a triple point. So I'll not be, perhaps perhaps this fellow might interact somewhere else, intersect somewhere else, and these two plots might intersect somewhere else. So I may not get a triple point in that case. But I'll be definitely able to reproduce some of these qualitatively. And if I get much better approximations to my gas, here also all you need is, where did it go? All I need is delta H vaporization, nothing more. Yeah. So if I get a better approximation than ideal gas, then I'll be better representing the solid vapor and the liquid vapor equilibrium. Right? Okay. Is that time for me? Too early. Okay. So essentially you can use the Clapeyron equation and get the phase diagram out of it. We've seen for a single component system. Okay. Now, there's also a classification of these phase transitions. So, going from one phase to the other is a phase transition. So, there's a classification scheme which was developed by Paul Ehrenfest. Okay. Now, this classification essentially says how this transition is occurring. There are a few kinds of transitions. We just talk of the two most basic ones. One is known as the first order phase transition. First order phase transition. The definition is easy to remember if you relate first with first. So, it so happens that the first derivative of the chemical potential is discontinuous. At the transition, right? Sorry? With respect to everything. Okay. Whichever derivative you take, that should be discontinuous. Now, let's see what are the derivatives we know. One, I definitely know volume. What happens to the volume when I go from a solid to a liquid, solid to a vapor? Increases. Is it continuously increasing or discontinuously? Yes. You have a small volume of the solid, and at the transition, suddenly the volume of the vapor is huge. So if I were to plot volume as a function of temperature, let's say I have a transition temperature. So I'll plot everything with respect to temperature. Here I'll plot volume. And let's say that's my transition temperature. So if I think of a solid vapor, for example, or a liquid vapor, whatever, other than water, take the general case. As I increase the temperature, the volume of most of the materials increases. So let's say on the left, I have the solid whose volume increases, and on the right I have a vapor whose volume also increases as a function of temperature and increases much sharply as compared to the solid. And there's a discontinuity over here. Suddenly the volume is too large, so the slope will be something like that. Right? There is a discontinuity at the transition temperature. The volume suddenly changes from that of a solid to that of a gas. I know another thing, for example, I know the entropy. That's another derivative. Well, actually, all of these quantities can be made to be derivatives of mu. Yes? No.